So we have the 1 times 10 to the minus 8 molar HCl, and our normal way of figuring this out would just be, okay, HCl is a strong electrolyte. From that we can figure out how much H plus we get, but it doesn't work. What we're missing here is Kw is a significant contributor. The reason this doesn't work is for dilute solutions or small concentrations of H plus, Kw is significant.
Do you have a preference if we use H plus as opposed to H3O plus?
No, I don't. You could use either. In chemical equations, I prefer H3O plus, but just for talking about pH and other things, H plus is fine. So, do you want me to go through how you would do this, or did you do it though? Did you plug it back in?
Basically, like, copy pasted the thing that you did for the first one,
Mm-hmm.
and I got 1,000,000% here. So I just had a slight feeling that I did it wrong.
Yeah, 1,000,000% error is not good. It's not. I told you do it set up exactly the same way, which you do, except the math is different. If we don't have a numerical value for K, then we're just going to make an assumption. A is very large, so we'll assume it goes 100%. So this is 1 times 10 to the minus 8 molar. This is nothing. This is nothing here and nothing here. And so we're going to assume complete reaction. 1 times 10 to the minus 8 molar here, plus 1 times 10 to the minus 8 molar here, plus 1 times 10 to the minus 8 molar here. And so at equilibrium we should have 0 molar HCl, 1 times 10 to the minus 8 molar H3O plus, and 1 times 10 to the minus 8 molar Cl minus. So what we do is we break this up into 2 steps. Step 1 is the acid, and then step 2 we do Kw here. And that is, we'll have H2O liquid plus H2O liquid. This is going to go to H3O plus plus hydroxide. Now Kw for this at 25 degrees C is 1.0 times 10 to the minus 14. So we have the number there. What we do is we reset this. We assume that nothing's hydrolyzed yet. And so I'm going to divide this into 2 things. So I'll say from water, nothing's hydrolyzed. So we have 0 molar and 0 molar. And so this is the second method I used. Rather than a Le Chatelier's type problem, I did a reset problem. So I automatically reset this.
Explain when we should reset.
For example, I look at the K here, and I know I'm going to reset it. This K is very small, and if it's very small, then it should be all reactants, which would be H2O liquid. But since the concentration of H2O liquid doesn't change, if I remove H2O liquid or add H2O liquid, the concentration remains the same. So we are getting some more additional H2O liquid, but since its activity, and we have to use activities for this, is 1, I kind of ignore it. And so normally in pure water, we have pH 7. pH 7 is 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide. In pure water, we call it pH neutral because the hydronium concentration and the hydroxide concentration are the same. So I know I'm going to reset this to the left. Now if K were big, I'd reset it to the right. You know, if it isn't already, reset. So if I were given this problem like 0 and 0, that's perfectly fine. We'll just start like that because that's going to ensure that the change is going to be small. If k were big, I wouldn't want to leave it like this. I'd want to reset it to the right.
So the side that gets the zeros is dependent on if it's k is large or small.
Right.
Okay.
Right. All right, that's from the H2O, but what we do is we add the HCl in there. And so I'm going to do this. Well, that's good, Ashley, that you worked on this problem afterwards. You don't want to wait until the night before the test to figure these out. And so from HCl, what we're going to do is we're going to take the hydronium that was produced in step 1 and have that as our starting hydronium in step 2. So this is going to be 1 times 10 to the minus 8 molar HCl. And then I have 0 molar hydroxide. And so now my initial from all of these contributions will be 1 times 10. So let's go back to black. 1 times 10 to the minus 8 molar hydronium. That's all from the HCl. And 0 molar hydroxide. The hydroxide is going to come from water autoionization. And so I'm going to have a change here. The change is I'm going to lose a little bit of water, and I'm going to gain a little bit more hydronium, plus X molar, and I'll gain a little bit of hydroxide. And so then at equilibrium, I should have 1 times 10 to the minus 8 plus X molar hydronium, and then X molar hydronium. And so Kw is equal to the equilibrium hydronium concentration times the equilibrium hydroxide concentration. And so we'll just plug it in here. We're going to have 1 times 10 to the minus 8 plus X times X. Now what I'm going to do is this. I'd like to reset it because that means that the simplifying assumption is more likely to be valid. And that's because the change should be small. We expect a small change. And so I'll go ahead and try the simplifying assumption. Okay, trying the simplifying assumption, we're going to assume that X is much smaller than 1 times 10 to the minus 8. And therefore, 1 times 10 to the minus 8 plus X should just be the same as 1 times 10 to the minus 8. And then we'll leave this X in here because X is big relative to 0. And what we're going to get when we do this calculation is X is going to equal Kw, which is 1.0 times 10 to the minus 14, divided by 1 times 10 to the minus 8. And so I'll use the properties of exponentials, bring that up. We get we're going to get 1 times 10 to the minus 6. 1 times 10 to the minus 6 is small, right? It's small, but small is relative to how much you start with. You know, if you start with, let's say $1 million, then $100 is kind of small, right? Relative to $1 million. Uh-huh.
So if the amount of hydronium that would come from the water is like so incredibly small, then like I'm a little bit confused on like what the point of finding it is. Like, does it ever really have a significant impact on?
No, this is very confusing for the calculations. You know, it's small, but we want to know how much it is. And so what we're going to do is we're going to calculate, you know, precisely the amount. When I do this simplifying assumption, it's going, a lot of people will say this. You know, if we're going to assume the change is small, then we're done. we're done. It's just 1 times 10 to the minus 8 here. It's negligible, so it's not going to impact anything, right? We're done. But that's not what we're after. What we're after is we're just using a trick of algebra. This is just the trick of algebra. This is not getting us the correct answer. This is just making it simpler. What I want to know is, yes, here I'm assuming x is so small we could ignore it. Then you're going, why? Then if you're assuming x is so small you can ignore it, then why not just take that as your answer? X is so small we can ignore it. No, we don't take that as our final answer. Our final answer is going to be an actual number. So what we're going to do is this. We're going to do a trick where we assume that x is very small and we ignore it, and then we solve for x anyway. And we solve for x and then we see, you know, is it really so small? And so this is not perfect math here, because we're actually calculating the wrong answer. This is an incorrect assumption. We want to know what x is, you know. And so what I'm doing is I'm just using the simplifying assumption to solve for x. This x is off a little bit. Now, we are going to determine, is it off by an acceptable percent error, or is it off by a large percent error? And so what we do this is just estimating. We aren't actually going to calculate the percent error. What we're going to do is we're going to calculate the percent change. And so we need to justify the SA. The way we justify the SA says that if we use the SA, which is wrong, to calculate an x value, which is wrong, is that x value going to be close enough, you know, that we'll accept it. And so we justify the XA by calculating the percent change. The percent change is going to be the change over our initial. So it's 1 times 10 to the minus 6. Our initial is 1 times 10 to the minus 8 times 100. So 10 to the minus 6 divided by 10 to the minus 8 will give us 10 squared times 100 is another 10 squared. So that's 10 to the 4th. And I end up with a 10,000% change. What's my max? 5%. And so what the percent change is, it gives you a ballpark, you know, of how much error to expect. But less than 5% is acceptable. Greater than 5% is unacceptable. And so what we see is that this is not acceptable. Uh-huh.
So what does that mean? That it's not acceptable?
What it means if it's not acceptable is you can't use this assumption. If we can't use the assumption, then we have to solve it the normal way. In other words, this is too big of a change, and therefore the error we expect is too large. And so we're just going to solve it using the quadratic equation. And so we'll get 1.0 times 10 to the minus 14 is equal to 1 times 10 to the minus 8 plus x times x. And so I'm going to put everything on the right side and flip it over to the left side. So this is going to be x squared plus 1 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 is equal to 0. So I got it into quadratic form. And now I'm going to plug this into my quadratic equation solver. And so let me bring up the quadratic equation solver here. So I have 1, and then this is going to be 1 times 10 to the negative 8. And this final one will be negative 1 times 10 to the negative 14. It was kW. And then calculate that, and let's see what x comes out to. So the two values of x I get, x is equal to 9.51249. I'm not allowed this many sig figs, but I'm going to carry some extra sig figs to try to minimize round off error. So 492. This is overkill, but I'm going to drop all the additional digits. And then we have an x equal negative value. The negative x value we can eliminate because in this case we can't go below 0. Sometimes we do get a negative value and it's correct. You know, when we get a negative value and it's correct is the case where we have the change in the wrong direction. So let's say you determine that the change should be left to right, but it turns out it was incorrect. Well, you can still get the right answer. You know, you'll just have to pick the negative x value, not the positive x value. .512. There's some something I'm missing there. Times 10 to the minus 8. .512 times 10 to the minus 8. So the equilibrium value we expect, we have 1 times 10 to the negative 8 plus 9.5. I'll just carry a couple extra. 512 times 10 to the minus 8. This is going to give me 10.512 times 10 to the minus 8. And so what we have is the HCl term is here. That's how much hydronium came from the HCl, step 1. X is how much hydronium comes from step 2. Which one's bigger? Yeah, it looks like X is a lot bigger. And so out of this 10, you know, like 10% came from the HCl and 90% came from water.
That's because the pH is so high. It's like said its pH is like 8 or something, which would imply that the concentration of HCl would have to be like very, very, very low. Which, you know, 10 to the minus 8.
Yeah, this pH of 8. It's
relevant to the problem at all?
It's relevant because if you got a pH of 8, this is basic. But HCl, is HCl a base or an acid? This is an acid. And so this is why it's impossible. An acid is not going to give you a basic pH, no matter how dilute it is. An acid is going to give you an acid pH. An acid pH is below 7.
I mean, my interpretation was that there were other ions that make it more basic, but those would interact with the reactions we're doing here, so...
Yeah, if there are other ions present, that could be very well possible. However, there are no other ions present. The only other ion present is chloride. But chloride is so weak, we call it neutral. We don't even factor it into acid-base calculations because of it. And so there's nothing else there. And so you can't have this pH here. It cannot be basic. It has to be acidic. So, before we get to that, though, let's calculate the K based on our equilibrium concentrations here. I have to order a new tablet. I have an extra one. I just can't find it right now. Okay, there we go. All right, so the hydroxide concentration is 9.512 times 10 to the minus 8. Okay, so this is important. Which is bigger, the hydronium concentration or the hydroxide concentration? The hydronium concentration is bigger. When we have more hydronium than hydroxide, we say it's an acidic solution, therefore acidic. All right, the first thing we do is we double check our calculation. How do we double check our calculation for the equilibrium values? The way we do it is by checking if these multiply out to our kW. This is 1.0 times 10 to the minus 14 is the correct value. And so what does this come out to? Can somebody punch this in their calculator? $10.512 times 10 to the minus 8 times 9.512 times 10 to the minus 8. All right, this is what I get. I got 9. I get equals 9.9990 times 10 to the negative 15. Which is going to equal 0.99990 times 10 to the minus 14. Do these match? Yeah. Yeah, it's pretty close. In fact, if I carried more digits, this is why I wrote more digits. If I carry these digits all the way out to here, it's probably right on. It just depends. This is due to round off error. Otherwise, it'd be right on. And so that's a check. This looks good.
I would have thought to move the decimal place one down. Like I would have just thought about it. Like, I made a mistake.
Oh, yeah. But then it's hard to compare because this is 10 to the minus 15, that's 10 to the minus 14. So you have to have them equal. So either change this. This would be 10 times 10 to the minus 15 versus 9.9. 9 times 10 to the minus 15. You got to make them equal, 10 to the minus 15 or 10 to the minus 14. So we have a match here, yes. Looks good. If you want to, if you're worried about it being a real error versus round off, you could just carry all the digits and then see how well they match. So the last thing is we do an inventory. If we have a beaker of 1 times 10, oh, actually, I need to do pH, but I'll do that after this. If we have a beaker that's labeled 1 times 10 to the minus 8 molar HCl, what's in it? Yeah, we're going to have actually hydronium. And the,
Hydronium and chloride.
Hmm?
Hydronium and chloride.
yeah, hydronium and chloride. How much hydronium do we have? 10.512 times 10 to the minus 8 molar. How much chloride do we have? 1 times 10 to the minus 8 molar. And do we have anything else? How much HCl do we have? Let's put that up.
Since it's a strong acid.
Yeah. So we'll write 0 molar. Do we have anything else present? Water. Yeah. Its activity doesn't change. Its concentration really doesn't change. And we have one more thing. What is it?
Hydroxide.
Hydroxide. That was 9.512 times 10 to the minus 8. So the hydroxide and the hydronium concentration are nearly equal. So this is almost pH neutral. The pH of this is going to equal the negative log of the hydronium ion concentration, which is 10.512 times 10 to the minus 8. So I'm going to punch that in. 10.512. Times 10 to the negative 8. Take the log of that, base 10. Technically, we're only allowed 1 sig fig because of the concentration here, but I carried extra digits. And so this, would you drink this? You know, when I was taking high school chemistry, my chemistry teacher used to talk about drinking hydrochloric acid.
Isn't that just what stomach acid is? Or
Yeah, that's what stomach acid is, but you don't want to drink hydrochloric acid. It'd be very bad. But he had one requirement, though. First, he had to add sodium hydroxide. So he's going to take the hydrochloric acid and then add sodium hydroxide and then drink it. And you know what he said? He said, well, it's going to be just salt water, right? Salt and water. He never did it, though. But you know, I drink this. I drink this without adding any sodium. In fact, I wouldn't want to add sodium hydroxide to this, probably kill me, but I drink this no problem because this is more neutral than our water. You know what our water is? This is what, pH 4? pH 5? pH 4.5? pH 5 is like 100 times more acidic than this. I mean, this is like pure water. And so 10 to the minus 8 molar, I mean, there's barely any hydrochloric acid in there. Right? And so it's very, very dilute. But take a look at the pH. Now it makes sense. The pH is less than 7. So if we have an acid, the pH has got to be less than 7. It can't be above 7. So that was a mistake. So when do we know we have to use KW or not? Let's say the question was, we're doing a pH calculation. When you have to use KW is if you have a very small amount of hydronium. Otherwise, we can skip it. Sometimes it's very easy. So when must Kw be calculated for pH? So an example is if we had 6 molar hydronium, do you think Kw is going to contribute anything to that? No. If we have 1 times 10 to the minus 8 molar hydronium, this is step 1, is Kw going to be significant? So here, Kw is insignificant. Here, Kw is significant. Mm-hmm.
If it's a problem when we know KW is going to be insignificant, you still want us to calculate it?
No, you don't have to calculate it, especially if it's just for pH. You can skip it. The most hydronium we're going to get at 25 degrees, the most hydronium we can get from Kw at 25 degrees C is 10 to the minus 7 molar. But because of the Le Chatelet's principle and having hydronium there to begin with, it's going to be much less. Will be much less. So it boils down to this. 10 to the minus 8 molar HCl, yes. How about 10 to the minus 7 molar HCl? Yes. How about 10 to the minus 6 molar HCl? Maybe, maybe not. Maybe it's like one part out of 100, 1 part out of 1,000. Depends. How about 1 times 10 to the minus 5 molar HCl? Probably wouldn't worry about it. You know. It's not going to be a very big contributor. If you're ever uncertain, just do it. Do the calculation, see how much additional hydronium you get.
10 to the minus 6 is the cutoff for what you should or shouldn't calculate.
Yeah, something around there. Depends on how precise, how many sig figs you're doing the calculation out to. If you're doing the calculation out to a lot of sig figs, then factor Kw in. If you're not doing it to very many sig figs, it's going to round off, give you the same answer at the end. Okay.
These are the questions only tangentially related, but when we take the exam, will we have formula sheets for all these things we need to memorize?
No. You're not going to have formula sheets. What I usually do is I just write it on the board.
Oh, okay.
So certain formulas and certain constants you don't have to memorize. You know. The pH equations you don't have to memorize those if you don't want. You know. Does that answer the question on
I
this?
think I stopped when I got like the 10,000%.
Okay. Yeah, that just means you can't use the simplifying assumption. So. All right, what are we doing today for lab? Today's lab is going to be synthesis of this K3 bracket CR parentheses OX3 solid. Well, what's this called? Oxalato, oxalato, it doesn't matter. It's fine. Yeah. What's the charge on the chromate?
Plus the
Roman numeral? Yeah, +3. Okay, good. So we're going to make this stuff. So what do we need to make this? What we need potassium ions. That's no problem. You can get potassium ions from lots of different sources. We need chromium-3 ions. The chromium-3 is also not a problem. We can buy chromium-3 nitrate or whatever. And we need oxalate ions. Oxalate ions, no problem. We can buy oxalate salts. We have oxalic acid. Plenty of oxalate available. But that wouldn't make a very interesting synthesis. So we're going to make it a more interesting synthesis. Chromium-3 is a very common charge on chromium. What's another common charge on chromium? Chromium-2. And there are some polyatomic anions of chromium that you probably have memorized. Do you know some polyatomic ions? Yeah, chromate and dichromate. And so let's talk about those. Chromate has the formula Cr, what is it? Cr O4 charge? 2 negative. That's chromate. And dichromate has what formula? Cr2O7 charge? 2 minus. And the weird thing is, when chemists look at these, they see the same thing. Although, do you see the same thing? I see, at least for redox, I see the same thing. What's the charge on chromium here? The oxidation state. This is +6. And the charge over here? This is +6. And so both of these are what we call chromium-6 complexes. They contain the chromium-6. Now, chromium-6 is not a free ion. It has to be stabilized with the oxygens. But we just call this chromium-6. The 6 here refers to the valence or the oxidation state. Valence is usually like number of bonds, that kind of thing. Charge. So in terms of redox, they are kind of the same. You know, in terms of redox, it doesn't really matter which form. You know, some might react faster or slower, but they're both chromium-6. You know, I gave you another example with nitrogen. Do you recall the example with nitrogen where you have 3, you know, totally different nitrogen-containing species, totally different, but they all had kind of the same redox? Do you recall what that was? Yeah, ammonia, NH3, ammonium, NH4 plus, you know, and others like methylamine, you know, and methylammonium, etc. They're going to have similar redox properties, at least for the nitrogen, and these should have similar redox properties because both of these are chromium-6. And we look at what is the range for oxidation states on chromium. And so let's take a look at chromium here. And so chromium's here. So what's the range of oxidation states for chromium? +6, you know, +6 is +1, 2, 3, 4, 5. +6 would be isoelectronic with argon. That's good. +6. Or Okay, so we got plus 6 or minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So minus 12 to plus 6, did you say? Well, actually metals really don't, metals can form anions, but they aren't that stable. It's better that, it's easier to oxidize them. I shouldn't say they aren't that stable, It's unusual to have a metal anion. And so what we have, especially to hold on to this many electrons, is not going to be possible for chromium. So what we say the oxidation state range for chromium is 0, the metal, to plus 6. 0 to plus 6. Metals tend to lose electrons, not gain electrons. That's what happens with all the metals. And so that means this chromium is on the electron poor side of things or the electron rich poor. And so the richest it gets is 0, and the poorest it gets is plus 6. And so this is the range. We're maxed out here. So these are electron poor. Electron poor species means they're going to be an oxidizer or reducer. Oxidizer. And so we know that chromium 6 should be an oxidizer, no matter what compound it's in. It should be an oxidizer. And the next thing is, how good of an oxidizer is it? Is this a very good oxidizer? And so this is where you need a little bit of memorization. And it turns out that chromium 6 is a good oxidizer. How do you know? These types of things are from experience. That is, you've seen it before or somebody's told you, that chromium 6 is a good oxidizer. What if you don't know? Then we can look up some data on this. Like, for example, we can look up data on dichromate. What did I do with my dichromate? Must have closed it. Or chromate. So a common compound is potassium dichromate. And this talks about its chemical reactivity and safety. And so here, there's an emergency telephone number. This is 24/7, 365. So any day of the year you can call this in case there's some kind of emergency with potassium dichromate, either health or hazard, as in physical hazard. So it's an oxidizing solid. It's also toxic by oral, don't eat the stuff, and inhalation. We used to use some powdered chemicals. Powdered chemicals are kind of hazardous because what happens is people generate dust clouds of this stuff and then inhale it that way. Whenever we're working with hazardous powders that can create this dust cloud, aerosol, we do it in the hood. However, we're using potassium dichromate today, which is orange solid. It's over in that corner over there. And it's pretty well granulated. That is, it's not too finely divided. And it has pretty big grains. So there's dermal, so watch out for skin contact. If you have gloves, use them. Otherwise, just avoid touching the stuff. Skin corrosion, serious eye damage, respiratory sensitization, skin sensitization. If you're working with this, some people work with potassium dichromate day after day, like leather tanners. Do you know what they use to tan the leather, to oxidize the leather? Well, I know they used to use potassium dichromate, to tan leather. So they could develop sensitivity to it. If you develop sensitivity, then any slight contact causes pain. So watch out. Although, we're not exposed to this on a daily basis. Carcinogenicity, be careful. So you want to handle this. It's a reproductive toxin. It's a mutagen, carcinogen. You want to handle it with care. It's like, this is similar to like gasoline. Gasoline, however, gasoline's not an oxidizer. Gasoline's a reducer, but it's also a carcinogen and mutagen. So it's like if you have let's say a bowl of gasoline, you don't want to place it next to your pillow and go to sleep. You're not going to breathe this stuff, right? It would be quite hazardous. The same thing with this. I mean, we can minimize exposure, and therefore, if we minimize exposure, in other words, we're just going to reduce our exposure to this. Just take extra precautions so that we can minimize the risk here. So there's short-term hazards and long-term hazards for this. This is aquatic hazards to aquatic life. Okay. But this goes into more depth, and so you could read this. Here. So we have these pictograms. Do you know what this represents? A fire. And then, do you see the O? Oxidizer. So this is going to intensify fires. Oxidizers aren't the fuel. Oxidizers are the oxidizer, like oxygen. And so may intensify fire. It's the oxidizer part of fire. So you need two components, fuel and oxidizer. This should be pretty obvious. This is pretty, toxic, poisonous. Respiratory hazard, corrosive to skin and other objects. Caution. And environmental hazard. You don't want to dump it in lakes or out. In fact, people used to dump it, dichromate. They use it for a lot of different things. You'll see dichromate in concrete mix. Once our next door neighbor was making a concrete patio, and it was a really windy day, and they created a dust cloud. And this dust cloud blew into my backyard and covered it with powdered concrete mix. And I was thinking, dichromate's everywhere now, So anyway, they used to dump it in ponds, and then eventually it contaminated drinking water. There's a very famous incident of environmental pollution, the dichromate in, I forgot the name of the city, but it's in the San Joaquin Valley, on the south end of the San Joaquin Valley. Have you seen that movie Aaron Brockovich? Or heard of it? Yeah. Apparently there was some kind of cluster, maybe cancer cluster or something. And turns out that the drinking water had high levels of dichromate or chromium-6 in there. And so, I haven't actually seen the movie, but I know that I've heard the story. All right, so in chemistry, we have to deal with a lot of hazardous substances. And so, there are a couple of things you could do. You could just don't expose yourself to any of this, or you can just take precautions when you deal with it. And so, like gasoline is hazardous, so you can not expose yourself, or you can just take precautions to minimize the exposure and minimize the risk. And that's the same thing we're going to do here. And so you'll probably ask your lab partner to get the potassium dichromate to save yourself from exposure. That's probably the safest method of dealing with this. Or just to draw straws, shortest straw, losers. No, actually, it's not. When you read these, a lot of these, it's like the same thing. If you read the thing for gasoline, you go, well, maybe I don't want to touch gasoline. Inhale. Okay. All right, so this is the SDS, or the, and it talks about what to do. You know, if swallowed, immediately call a poison center, doctor, rinse mouth. If swallowed, you know, sometimes some things you want to drink milk, some things you want to drink water. Other things you take other precautions. So if swallowed, rinse mouth. Do not induce vomiting. If on skin or hair, take off immediately all contaminated clothing. Rinse skin with water, shower. You know, we have a shower over here in the corner. So if you get a lot on yourself, you want to go here and immediately take off your clothing, contaminated clothing, and take a shower. We've had incidents like this in the past where people don't want to do that. And so they let it continue to contact their skin, and it's corrosive. And so it can cause damage. So fortunately, we have this, so you can do immediate, you know, just wash it off. You don't have to take off your clothing, although there's a safety video which shows you should take off your clothing, right? You've probably seen it. But anyway, we have this, so initially wash it off, or this is kind of far. There's a safety shower that might be closer to you. Do you know where it is? It's these handheld ones. These ones. You're familiar with these? Yeah. These are eye wash fountains, but you can use these as safety showers as well. And so each sink has that. And so use that to get the initial contact off. And then after that, we decided, this happened in our old building. This happened in our old building where a person spilled a whole bunch of sulfuric acid, the concentrated stuff, on their jeans, but didn't want to take off their jeans. Ended up getting severe burns on their legs, like 3rd degree, 2nd degree. They went into the women's restroom to try to wash off the concentrated sulfuric acid from the sink, but the sink doesn't supply very much water. And so during all that whole time, the burning got more and more intense. And so after that incident, in this building, we have a private shower. And so there's a private shower. You don't have to, so you do the initial here, and then you can go to the private shower and remove contaminated clothing to make sure you get all the chemical off your skin. So safety shower, eye wash fountains. What happens if you get it in the eyes? If in the eyes, rinse cautiously with water for several minutes. You know, this is some kind of rule. How many minutes do you, it says several minutes, but most people say you should rinse for 15 minutes, right? 15 minutes. That's because an eye is like a sponge. So rinsing off a wet sponge, it's not so effective and efficient. And so usually 15. Remove contact lenses if present and easy to do so. Continue rinsing. Immediately call a poison center doctor. If exposed or concerned, get medical advice attention. If skin irritation or rash occurs, get medical advice attention. If experiencing respiratory symptoms, call a poison center or doctor. This is obvious. Wash contaminated clothing before reuse. Do that. In case of fire, use dry sand, dry chemical, or alcohol-resistant foam to extinguish. Okay, collect spillage. If there's a small spill there, you know what we do? Just get a wet paper towel and wipe it off. Use gloves if you have them. If not, just use lots of towel and wipe it off. And the dichromate should oxidize the paper in the towel. If it oxidizes the paper in the towel, it's going to convert it from chromium 6 to chromium 3. Chromium 3 is a lot less hazardous, so we can live with that. And so the chromium 6, when you use the chromium 6, be extra cautious. Okay, over there we're going to weigh some out into a beaker, so you'll just tear a beaker. And it's pretty easy to have your risk of exposure down to 0. I mean, there should be no reason you inhale this or no reason you touch it, you know. And it should be easy to do. So that's one of the skills. One of the skills we do in chemistry is we learn how to work with hazardous materials without poisoning ourselves or without causing accidents. Okay, so that's it. But in our synthesis, we don't want chromium 6. But let me talk about one final thing. Not only is chromate and dichromate similar in terms of redox, they're actually the same thing. You know, when people think about chromate and dichromate, they're kind of interchangeable. And the way they're interchangeable is like this. If you have one chromate, a chromate is a tetrahedral
ion, like this. I'm not going to draw out all the lone pairs. Or maybe I should. So that's our chromate. And we want to make dichromate now. And so what I'm going to do is I'm going to take two chromates and then attach them together. And how should I attach them? The way I'm going to attach them is I'm just going to link the oxygens together. Like so. But do you see this bond here? What kind of bond is that? We give a special name to this bond. What is it? Yeah, this is called a peroxide bond. And what do you know about peroxide bonds? They're highly unstable. They're highly unstable because they're very weak. They only require 147 kilojoules per mole to break. Mm-hmm.
What happened to the other pair?
They disappeared somewhere. I'm not keeping track of them. They're still there. They're still there, but I don't want to talk about the charges of the metal. Uh, 147 kilojoules, visible light can break this. So, I mean, this is like a chemical you have to protect. This chemical can only come out at night, you know. Or if you work, maybe if you work in a dark room, maybe red light won't break it. Maybe if we switched all the lamps in here to red, you know, maybe that would work.
Are dark rooms red because red is like the least short wavelength of light, so it's
Yeah.
makes sense.
Dark rooms are red because red is the least energetic visible light.
Yeah.
So it doesn't form a peroxide link. You know, there are some things, reference points that you want to know. You know, 147 kilojoules is on the low end. What's on the high end for covalent bonds? Covalent bonds range from what to what? A 100 kilojoules per mole on the low end to 1,000 kilojoules on the high end. So on the low end, you're going to have like peroxide, iodine. Iodine's a very weak bond. Iodine has to be protected from light. On the high end, do you know what has a bond energy of around 1,000? What's the strongest covalent bond you can think of? A triple bond, yeah. A triple carbon? Not carbon, the one I'm thinking about. As oddly enough, a triple bond in carbon, the one I think of is acetylene. Acetylene's very dangerous. It's highly flammable. It's quite electron rich. And this is redox. But the one I'm thinking of is this. What was it, Ashley?
It's nitrogen.
It's nitrogen, yeah. Now think about this. If you have peroxide or if you have iodine, you're going to protect it from light. And so you need a bottle that is like brown or black. It doesn't let any light pass through it because it's so reactive. But if you have nitrogen, it's so unreactive, we don't even pay any attention to it. We don't, I mean, the air that you're breathing, you know, most people worry about how much oxygen is in the air, but do they even care about nitrogen? You know, each breath you inhale is 80% nitrogen. Do you even worry about the nitrogen? Is the nitrogen doing anything? No, the nitrogen's doing nothing because it's what we call a pseudo-inert gas.
I mean, doesn't it require like advanced biological
Enzymes to, yeah.
enzymes to break down?
Right, exactly. Legumes can do it, but, you know, other things.
I think it's the legumes that do it, it's the
No.
bacteria, right?
Or the bacteria, whatever it is. Yeah, I don't know. Or the other way you can get nitrogen to react, you know one way to get the nitrogen to react? In air? Diesel engines. This is why diesel engines are bad for the environment. Diesel engines are bad for the environment because the nitrogen in air will react with oxygen in air at high temperatures and high pressures. And do you know what they form? NOx, NOx. And so diesel engines produce lots of oxides of nitrogen, and a lot of diesel engines have no emission control. Like all the ships, they're just burning, and the NOx are being spit out. A lot of diesel trucks are spitting out lots of NOx. You know? And so those are gross polluting vehicles. And that's just because the nitrogen it's so hard. Automobile engines potentially can produce NOx as well, but not to the extent that diesels do. But nitrogen's pseudo-inert. It can react under extreme conditions or with bacteria or whatever else that has certain enzymes that can help break it down. Otherwise, 1,000 kilojoules is too much. And when we have 100 kilojoules, it's highly reactive. Highly reactive, it's a weak bond, so hydrogen peroxide is quite reactive. So what we need to do is this. What we're going to do is we're going to take two chromates, but we're going to try to eliminate an oxygen. In other words, what we're going to try to do is we're going to try to link it with just one oxygen. And this is called a bridging oxygen. Bridging oxygens are no problem. This is like water, you know. And what we end up with is this. We end up with Cr2O7, 2 minus. So dichromate has an odd number of oxygens, and that's because we're trying to avoid the peroxide link. But how do we get rid of an oxygen? Can you tell me one way to get rid of an oxygen in a chemical reaction? Make it bond with something else. And what's commonly used to get rid of oxygens? I mean, you could use carbon, but there's something else that's commonly used to get rid of oxygen in chemical reactions, in compounds. Just an oxygen atom. Let's say I have 3 oxygens and I want to get rid of 2 of them. Have you seen that before? Yeah, let's say, you know, this is what you do when you know, you don't necessarily do this on the first reading, but let's say you've read through this a bunch of times, and pretty soon you start getting bored, and you start thinking, what's going on here? So what's going on here, let's say I have 3 oxygens, and I want to get rid of 2 of them. So if I start off with nitrate, and I want to end up at nitric oxide, I have to get rid of how many oxygens? I have to get rid of 2 oxygens, 2 out of the 3 oxygens. Well, how do they do it in this reaction? Do you see how they did it in this reaction?
Yes.
They reacted with, H plus. So we're getting rid of 2 oxides essentially, and we're making dihydrogen monoxide or water. And so that's one way of doing it. We can use H plus. And in fact, this is quite common. Look at here. I have iodate with 3 oxygens, and then I have iodine with no oxygen. So I need to get rid of 3 for each iodate, and I have 2 of them. So I need to get rid of 6 oxygens. How many hydrogens do I need? I need 12 hydrogens to make
6 waters. And so this is a pattern that's repeated over and over. MnO2, 2 oxygens, was going to require how many hydrogens? 4. 7 oxygens on dichromate, I want to get rid of all of them. So if I have my dichromate and get rid of all the oxygens, then how many H pluses will I need? 14. How many waters will I form? 7 waters. Do you see this pattern? This is one of the patterns, you know, you might not see it initially, but after like 10 times of looking at this, then it kind of stands out, you know. It's hard to see initially, but it's that repetition, you know. Or sometimes people just miss it entirely. You know, they're blind to the pattern. But anyway, let's go back to this. And so this is what I'm going to do. I'm going to take 2 dichromates and put them together. So 2 dichromates, or no, 2 chromates, sorry. I'm going to take 2 chromates and make it a dichromate. If I make it a dichromate, I need to get rid of how many oxygens? 1. So how many hydrogens do I need? 2. So I'm going to do 2H plus here. And that's going to make how many waters? 1. And then we're going to use some Le Chatelier's principle for this. As the H plus increases, which way is it going to shift? Left or right? Right. And so we expect to shift right. And that's going to favor a formation of dichromate. Dichromate is orange. Chromate is yellow. And so if we use this last week, we just add some acid to this and it turns orange. At low H plus concentrations, it shifts left and then it favors what? Chromate. And so at low pH, which is more acid, low pH is more acid, it's orange. At high pH, which is more base, less hydrogen ion, it's yellow. So when people see chromate and dichromate, it's the same thing. Chromate and dichromate are the same thing. It just depends on the pH of your solution. If your pH is high, you're going to get chromate, yellow. If your pH is low, you're going to get dichromate, orange. And so this is a Lewis acid-base reaction here that occurs between these. Whereas the table I showed earlier, these are all redox. So it's a little different. Lewis acid-base versus redox. These are all redox. So what we're starting with is the orange stuff there. And so let's take a look at the synthesis here. We're going to break up the synthesis into 3 major steps. In step 1, is we're going to convert from chromium 6 to chromium 3. So chromium 6 is quite a bit more toxic. Chromium 3 is quite a bit less toxic. So once we do this, it'll be good. But let's get rid of the chromium 6 first. Getting rid of the chromium 6, which form are we using? We're using the orange dichromate form, not the yellow chromate form. And so we're going to take our dichromate and then reduce it. So we need some kind of reducing agent. But we have to worry about, let's consult the SDS. If we consult the SDS, let's see what it says about it. This is toxicity data. Toxicity data. There's chemical reactivity data as we go down, down, down. Advice for firefighters. This is long. There's a lot of information here. So we go here, 10.3, possibility of hazardous reactions. risk of explosion with iron. Iron's a pretty decent reducing agent, so watch out. Magnesium's even better reducing agent. Hydrazine is an amine. Amines like ammonia, like ammonium, etc. So it could be hydrazine or derivatives. Derivatives would be the ammonium salt of that hydrazine. Hydroxylamine, ammonium. Remember, ammonium and the amines and ammonia are all kind of the same in terms of redox. They're all electron rich. Nitrate's electron poor, but ammonium's fuel. These are all fuels here. Boron, acetic anhydride, oxidizable substances. Oxidizable substances are reducing agents. In fact, they just put reducing agents here, and that pretty much covers it. Pretty soon this turns into weird mix mash. Like sulfuric acid. Sulfuric acid is not that great of a reducing agent. Silicon, exothermic reactions, so versus explosive reactions with anhydrides, phosphides, sulfides, nitrides. You can always have an explosive reaction. Depends on the conditions. So, for example, have you heard of those like grain silo explosions or bakery explosions? You know, it just depends on the conditions. Like that flour or sugar can explode with oxygen, or it might react slowly with oxygen, depending on how finely powdered it is and what kind of dust cloud you have. And so, a lot of these have a risk of explosion. So we need to be careful. And so we're going to pick a reducing agent that's weak. Give me a weak reducing agent. Give me like one of the weaker reducing agents that you know, that way we reduce the risk of explosion. Fluoride is pretty weak, but you know what it generates? If you oxidize fluoride, you generate fluorine. And have I taught you the fluorine chemist handshake? No? Yeah, lost fingers. We don't want to use fluoride. And fluoride's pretty hard to oxidize. Actually, chromium-6 is not enough to oxidize fluoride. Actually, the zigzag relationship. If I tried to oxidize fluoride, is that uphill or is that downhill? Yeah, that's uphill. Even though fluoride's very weak, we can pick other weak ones, but they might not react. What we need is something that is weak but could still potentially react. What's weak but could still potentially react using the zigzag method? If I have chromium-6 here, dichromate, I could use manganese-2. Manganese-2, but the problem is this. If we form manganese-4, there's a problem with potential manganese-4 precipitate like this, manganese-4 oxide. So I'm not going to do that. So we could use iodine, maybe make iodate. Bromide, the bromine liquid. And we could use some of these, but we're not going to use any of those. In fact, the reducing agent, we want a weak reducing agent, and the reducing agent we're going to use has a secondary purpose, and so this is why we're going to use it. We're going to use oxalate ion, and we have two sources of oxalate. We can use oxalic acid or we could use potassium oxalate. Oxalate is poisonous too. Oxalate precipitates out with calcium and makes stones, like kidney stones or some kind of stone, which would cause health issues. So don't eat oxalate, don't eat oxalic acid, don't eat potassium oxalate. It's toxic. Okay, yeah, good. I'm glad.
Is there anything we can't eat?
No, there's nothing to eat in here. Although I don't ask me why this happened, but I saw somebody taste the product of something. They're pretty desperate and they tasted something. This is during qualitative analysis. Yeah, maybe I applied too much pressure on them. All right. Normally, when I think of oxalate, I don't think reducing agent. You know what I think? What's the oxidation state of carbon in oxalate? +3. And we know that carbon ranges from what? Yeah, it ranges from +4 to -4. So if we're at a +3 oxidation state, we're on the electron poor end of the spectrum. This is electron poor. If oxalate's electron poor, I expect it to be an oxidizer. Versus a reducer. Because if it acts as a reducer, it can only lose one more electron. Do you see that? And losing it's not going to be so easy. And so I would think of this as electron poor. I'd expect it to be an oxidizer or a very weak reducer or weak reducer. And the reason I'm saying it's a weak reducer is because it's on the poor end. A strong reducer would be on the rich end of the spectrum here. But you know what? This is perfect for us because if we have something that's very weak, we don't have to worry about explosions. Yeah. But regardless, you still have to be careful with this because it says to slowly mix them together. And what a lot of people do is they just dump it together. And when they dump it together, then they get a violent reaction and it spills out all over the countertop. It fortunately does not explode in their face, but it splatters everywhere on the counter. And so be careful with that. Don't dump it all in at once, you know, and then it's going to create a mess. And so just slowly combine them. And then from this, what we're going to get is kind of a vigorous reaction. And it's going to form chromium 3 plus. That's what we want. So we're going to do this. We're going to remove a whole bunch of oxygens there. So we need some acid. Right? We can get the acid from oxalic acid. And so this is why oxalic acid is good. It has H+. You can get rid of some of the oxygens there. We need 14 H pluses to get rid of those 7, right? And then we can get the electrons from the carbon in oxalate. Okay, so this is a redox reaction. Do you know what the other product is? If you completely oxidize carbon to +4, what's a common +4? Carbon dioxide. So watch out for carbon dioxide. You watch out because it could effervesce quite violently. That's how it spills out onto the countertop. All right, that's step 1, the redox to form chromium 3. Step 2, we're going to complex our chromium 3 plus with 3 oxalates. The oxalates are going to come from primarily potassium oxalate. Maybe oxalic. If we have, you know, depends on how much excess oxalic you have in there. C2O4. And we're going to form this. The trioxalato chromate ion. And so reaction 2 is just Lewis acid base. We'll heat it up too to help chelate it. And then reaction 3 is going to be metathesis, but it's going to be kind of an odd metathesis reaction. What we're going to do is we're going to take 3 potassiums. There's plenty of potassiums around, and this. And what we want to do is we want to precipitate it. Uh-huh.
The top where you said that it was 3 plus? Why is it 3 minus?
I made a mistake. Each oxalate's a -2. And so that's -6 altogether, plus 3 from the chromium, gives us 3 minus. Sorry. Potassium salts are soluble. So how are we going to get this to precipitate out? One way we could get this to precipitate out is to evaporate all the water. But if we evaporate all the water, do you know what else is going to precipitate out? Any excess oxalic acid. Oxalic acid is a white solid. Any excess oxalic acid, any excess potassium oxalate will also precipitate out. And so we want to leave all those in solution and just precipitate out the complex. The way we're going to do this is we're going to do this by solvent exchange. It turns out that this complex is relatively insoluble in ethanol. Ethanol, I'm going to abbreviate ETOH for ethanol. So what we're going to do is this. We're going to have a certain amount of water. It's fixed. And then we're going to keep adding more and more ethanol. The more ethanol we add, the more ethanol-like the solvent is, and the more this should precipitate out. And so it's not really exchange. We're just going to dump in ethanol. And we're going to exchange it in the sense that the main solvent used to be water, and now it's mostly ethanol. In mostly ethanol. And then we're going to cool it in an ice bath. And an ice bath is going to decrease the solubility even further. So I'm going to modify the procedure a little bit here. After heating this, to complex it, then we're going to let it cool down, and then we're going to add some ethanol to this. What I'd like you to do is add a little bit of ethanol and see if you get some. Okay, actually, before you add the ethanol, make sure everything's dissolved. What I mean by this is the oxalic acid isn't very soluble. Don't worry about getting it all to dissolve until the reaction's complete. And so initially you might have lots of oxalic acid in there as a suspension, but by the time you get to this point, all of it should be dissolved. And so what we should have here is a solution. There should be no solid in there. That's very important. Okay, if there's no solid in there, then we're going to add the ethanol, and then we should start seeing some precipitation. And what we want to do is, in the past, all you try to do is get precipitate. And so you get tiny, tiny crystals, and you get like cloudy white precipitate. Have you seen those? Yeah, probably. Our precipitate's not going to be white. But what we're going to get precipitate, but for us, we don't want lots of tiny crystals. Crystals that are so small you can't really see them. What we want to do is we want to grow big crystals. And so what we want to do is we want to control the precipitation. That is, I don't want a whole bunch of precipitation, i.e. rapid precipitation right at the beginning. What I want is I want to precipitate a little bit and then stop. So add a little bit of ethanol, and if you start generating lots and lots of precipitate, then stop. Don't add the full amount of 10 milliliters of ethanol. If you don't see any precipitate at all, then maybe add a little bit more ethanol. But what we want to do is we want to grow a few crystals initially, and then let those slowly grow into big crystals, rather than trying to grow a whole bunch of crystals rapidly and they're all tiny. And so what we want is we want a few big crystals versus hundreds of small crystals. Uh-huh.
Sorry, where are we getting the potassium ions again?
The potassium ions are present from potassium oxalate. We're going to dump in both oxalic acid and potassium oxalate in there. And so there are going to be plenty of potassium ions to precipitate this here. Not only that, the dichromate too, we're going to be using potassium dichromate. And so we have potassium ions from both of these species here. Uh-huh.
Is this just going to be a qualitative lab or?
Yeah. Well, it's going to be quantitative because we're going to measure our what we call our percent yield. You know, our percent yield, we'd like 100% yield, but we're going to sacrifice our yield. You know, we could get 100% yield maybe with tiny crystals, but what we're going to do is we want big crystals. And so we want a higher purity, you know, like a higher quality. And then we don't care about the yield. If we get an 80% yield or 72% yield, it's not a big deal, as long as we get nice big crystals.
So is that
out
like
of
the
it.
only calculation we're gonna do?
Is the percent yield? Yeah. That's like percent. It's just to tell you, you know, roughly. But these reactions should give you a fairly high percent yield. All right, and then we're going to stop here. So to allow these crystals to grow, what we're going to do is we're going to add the ethanol, maybe get a few crystals, maybe get nothing. Let's say you add the 10 milliliters, it's okay, and you got nothing. Just cover it with a watch glass, put it in your drawer. Okay, and then we're going to come back and check it on Wednesday, and hopefully we'll get some crystal growth occurring. If we get big crystals by Wednesday, then we'll filter it. If we don't have big crystals by Wednesday, then we're going to wait longer because the crystals take time to grow. Okay? But what we want to do is we want to allow the crystals to grow bigger and bigger. And that gives a higher purity. It gives a higher purity because, you know, you get less surface area, you know, and inside the crystals, there's a specific site for each crystal ion, and if you have impurities, they get locked out of the crystallization process. So this should be good. All right, any questions regarding this? Okay, you're going to work with your. You can work individually if you prefer, or you can work in a group. You can work in a group of up to 3. You might want to work in a group of up to 3 because this lab you're going to have to write a formal report, and so if you have a group of 3, you can spread the work out amongst the members. Or 2 if you prefer not, or 1 if you just prefer not to deal with groups at all.
We're doing a formal report as a group thing?
As what?
We're doing like a formal report as a group?
Yes.
Okay.
Yeah, you're going to do a formal report as a group. So each member of the group will be co-author. You're going to turn in 1 formal report per group, kind of thing. Okay. Uh-huh.
What lab is this called in the like folder of labs?
This is called synthesis of a complex or something.
I don't see it in there.
Coordination compound.
Yeah, there's coordinate complexes as well.
Coordinate complexes lab. That's it. Reaction number 1.
Oh, yeah, that's.
All right, and then today I'd like to take a look at your observations before you leave. All right, that's it for discussion. Starting.
Take a look at the operating like this last day.
Yeah.